Today we have with us Jetharam, Mehramram, Bhambhu. He'll be talking to us about the relationship between greedy algorithms and Metroids. Uh, he is doing his master's thesis in at IIT Delhi. So you can start now.
Hello everyone. Today as Praneeth said, I will talk about Matroids. So Matroid is a structure on finite sets, and which was given by first given by Whitney in paper in 1938. It was mainly inspired from linear algebra. So we will go like how it is independentness from linear algebra. Like we know that when we call vector are independent, and so like in a 3D vector space we have independent vectors. And three-dimensional space we need three vectors to span whole space, and we call them bases. And there can be multiple bases for a given space. So from that, she got inspired and she wanted to generalize it in some way, like in more general way. So first, I will give you the definition. So in Metroid, we have a ground set. Let's call it E, and uh, and a Metroid, which we will call throughout this presentation I. So and we represent Metroid M as E, comma I. So I is collection of subsets of E such that if S is a subset of I, then it's every subset is also subset of I, Metroid. And if S and T are two sets in Metroid, and one of them have like less cardinality than other, then there exists another element E in T but not in S, such that S union E will be in Metroid. And we call first property as downward property, extend property. There are many other names for it. So this is the definition, but I will try to give you motivation like how we get to here. It won't be there. It's just it won't be that useful. No, it will be useful, but not that why exactly we are doing this. And another notational thing that we call elements of Metroid a independent set, and you will come to know why we call this elements of Metroid as independent set. So let's take an example for motivation. So this was given by Whitney in paper in his or I don't know. So let V be set of vectors in R3. V is our what's called V is our ground set here. Mm. So we once again. So we have this 8 vectors. Seven vectors are there in three-dimensional space. And let me construct a set with a set of all subsets which are independent, linearly independent. For example, A is a subset of V, which is linearly independent, such that B, C, D, E, F, G, AB is linearly independent, BC is linearly independent. So we are taking all these subsets of V such that they are linearly independent among them. So this is our Metroid structure, this inspired Metroid structure. So let's see which properties are satisfied by it. So we can see that I that we created is not empty. And another property that if let's consider set, let's take this set ABC. In our set, ABC belongs to I, and then we also know that AB, BC, and AC should also belong to I. As we can see by our property of linear algebra, like if three vectors are linearly independent, and so subset of them also will be independent. Simple linear algebra. So AB, BC, and AC are also part of the Metroid. And then if let's see A, B, C belongs to I, and let's take another set which is let's take CD. These two independent set let we take belongs to I. So as you can see, these both are independent set. The second set's cardinality is less than first set's cardinality. So so we know that if we exchange A, B, and D, if we take A, B, and D, it will be linearly independent. We can. Am I right? One second. Sorry, A, B.
I have a small doubt, Jeta.
Yes.
Yeah,
Yes.
so just to confirm, in terms of sets, when you mean linearly dependent, what do you actually mean? Like when two sets are linearly dependent?
So first I will define linearly independent sets. Linearly independent sets mean the elements of the set are linearly independent in vector linear algebra sense.
Oh, okay. So like if I have a set A comma B, another set has A plus B, then they are dependent like that.
Yes. So remaining remaining from independent set are dependent. Like as you can see here, let's take A and B.
Okay.
We will make the set A and B linearly independent.
Okay, yeah.
Then they will be part of the matroid.
Oh, okay.
I think the confusion is like you are saying that two sets are linearly dependent or independent, right?
He's
Okay,
talking inside a set. Okay, now I understood. Yeah.
So I was saying that two sets which are independent set, like the element of this I, an element is also called an independent set.
Okay, understood now. Now I thought you were comparing among sets. So inside a set, the vectors should be independent. Then they become part of a matroid. Okay.
Yes. And by nomenclature, each set is an independent set.
Okay. Yeah, understood. Thank you.
Yeah. So we have CD belongs to I, ABC belongs to I. So we will have, there at least exists one element which doesn't belongs to CD. Let's take for I. So A, C, D will be our another independent set. So this is our second property, exchange property. So this structure of independent vectors give motivation to matroids. So this was motivation. Like any doubts till here? Like exactly why Whitney wanted to do it, I don't know, but like she got motivation from this. Like she want to generalize idea from linear algebra to in some discrete structure, and also ground set E should be finite. Yeah. Okay, let's move forward. So we will talk about linear matroid. So in matroid, what we need? We need a ground set and its corresponding set which contains independent subsets of the ground set, which we call the independent set. So linear matroid is let V be its ground set which contains elements which are which are X is a vector such that X belongs to Rn. So what will be the matroid here? A subset of V such that vectors in A are independent. Like vectors in A are independent. Like the structure that we initially discussed, like the motivation, the structure that we call it the linear matroid. So we will take finite numbers of vectors from Rn, and independent the matroid will have subsets of V such that all the elements in the set are subsets are linearly independent. That is our linear matroid. Now the graphic matroid will help you to understand like how we will be using in greedy algorithm and all. Let's G equal to V comma E we are graph, and E, the H set is our ground set, and the matroid structure here I is uh, let me take A subset of E such that V comma E, V comma A is a forest. So can you see that? So H set is a ground set. We take a subset of H set, and then we consider the graph containing all the vertices and that H set, and that should be foreign, which means it does not contain cycle. So, and why this is helpful? Like everybody knows Kruskal's algorithm, max spanning tree, min spanning tree. Yes. Okay. So in Kruskal's algorithm, we are given graph with some edges with weight, and we want to find max spanning tree or min spanning tree. So we are finding tree. So tree is also forest by definition. So this graphic matroid will help us to prove that the greedy algorithm works in Kruskal's greedy algorithm works for max spanning tree, the Kruskal's algorithm. That we will do by the end of part. So this matroid structure we have on graph. Now there is another matroid, partition matroid. So we are given a ground set and a partition of this ground set. Okay, EK. So this is some partition initially given to us, and the matroid structure is A subset of and sorry also we are given K numbers. DI mod EI. So we are also given K numbers corresponding to each partitions, and they are less than equal to the cardinality of that partition and greater than 0. Greater than 0, greater than equal to 0. I am confused, but we can take both of them. It won't matter. So the matroid structure here, it will be A subset of E such that A intersection EI cardinality should be less than DI for all I. So such subsets will form matroid. So these are a few examples of matroid. Yes, and there can be many more examples, but these are few. Let's like any doubt here till like for these 3 given examples.
So the matroid of a like linear in the linear algebra sense, it's not finite, right? Like
it should be
like,
finite. Like initially I mentioned
like okay.
Like whatever I am defining here, like I haven't mentioned, the E, the ground set should be finite.
So like my doubt is like for when V is a vector space, like it can be like X, okay, like V1 to Vn be basis, then like V1, V2 are independent and V1 2 times V1 2 are also independent. So
here V is not a vector space. V is a subset of a vector space. Achha, okay, my notation is problematic, I guess. Yes, okay. So I should write.
Oh, I thought V is Rn. Okay. Huh.
V is subset of Rn. I think this works, right?
Only subset.
And now.
Oh, okay, fine, yeah.
Yes. Sorry, it was. I thought I mentioned the finiteness that might make that will imply this, but no problem. This is exact notation. Now, any doubts?
Yeah, understood. Yeah, thank you.
Yes. So these are few matroids, and there is some uniform Matroid, and so there are many more Matroid, and it have vast applications. And so in linear algebra we have basis, and we got inspiration from linear algebra for Matroid. So Matroid structure also some basis. So an independent set is just an element of Matroid, is called basis if that doesn't exist another set which it contains, which contains the bases. And so there will be many bases. So can you by intuition or by some logic can you say ki, why all bases should have same cardinality?
The second property of the Matroid.
Yes, suppose there doesn't, then by contradiction there will be another set which it contains. So all bases will have same size. Yes. So that also that is very intuitive from the motivation we got from, because the size of bases in our linear algebra is same. Like for in three-dimensional space, bases will have size 3. Now let's get to the work where we will use greedy algorithm. In greedy algorithm we make local decisions and we want that local decisions should accumulate and will give global optimal result. We will take local optimal decisions, then accumulate them, then we hope that we will get optimal in globally. That's what we do in greedy algorithm. So now let me define few things, then we will discuss the algorithm. So we are defining a weight function, any weight function on each elements of ground set E, and for subset for a subset belonging to ground set, the weight of that subset will be the sum of the weight of elements. This is the definition. And now we want to find maximum WS, maximum weighted subset, such that S is an independent set. We want to find this set. So everybody got our aim, like what we want to do. So if anyone can suggest me natural greedy algorithm that we can use here. Just natural greedy algorithm.
We can try to get the elements with the max weight, and then look at the size 2 sets that contain this element, and look at the max weight among them, and go on doing that till we reach the max size.
There is one another condition that we have to check always. Like what we have to check, the set should be okay. You are saying you want to check from every set of independent set. Okay.
Not exactly. Yeah. True. Okay.
Okay. That's the algorithm. First algorithm, without loss of generality, I would assume that weights are arranged in decreasing order. So algorithm starts. So we will first define our our input is E, comma this and this. So we are given this input, output. So our algorithm will be, we will define a set. First we will define it as an empty set. Then for I in n, like some Pythonic language I am writing, for I in range, how should I write this? Like for I in 1 to n, we will say that S if plus okay, 1 second, like some notational mistake here. I want to see. How should I represent? Like element corresponding to this will be E1, element corresponding this will be E2, and element corresponding to this will be En. So I will add Ei. If Ei belongs to it belongs to Matroid, then we will say that S then S is equal to S plus Ei. Everybody got it? Like we will enumerate over all elements from max weight, and we will add each element in our like the set that we want to make, and check if it belongs to independent set. So if it is an independent set, which means an element of Matroid, we will add it to our element that we want to create. So this is the greedy algorithm. And now, as you know, greedy algorithm doesn't work always. So now we want to know when this algorithm should work. Like for some weight function, this might work. Suppose we will take linear weight function, like depends on the number. A simple like identity weight function, that then this will work. And if we take in general and we will give a good Matroid structure for a given Matroid, this might work. But how can we tell that this will work always? So that we will prove now. Did everybody got the algorithm? Like it's very simple algorithm. Everybody got the algorithm?
I
Okay.
think yes, yeah.
Okay, yes. So it's simple only. So the main theorem, the main attraction here is, like it was very surprising for me that we have some structure for a greedy algorithm. So the algorithm that we gave here, this is a greedy algorithm, and it is like most general greedy algorithm. Like whenever you come up with some problem and you want to use some greedy algorithm, you will use isomorphic structure. This is similar, not exactly same structure but different language. You will use similar algorithm whenever you try to use greedy algorithm naturally. And so for this algorithm, for any weight function can be any. So greedy algorithm returns max weight base. Here why I have written base. So I would like you to check that the set S we are creating will be a base that you can check. This algorithm will give a base only. So we initially wanted to find an independent set, but that independent set will be base that you can check. So greedy algorithm return max weight base for any set of weights. This if and only if the underlying structure is a Matroid. So this was very surprising for me, and but it works. First, should I give you the proof, or should I give you the Kruskal's algorithm's example? Like if should I prove the Kruskal's algorithm?
Yeah, Kruskal's will be better.
Yeah. And just want to know, I forgot the definition of what is base.
So, base is we will have so many as independent sets from Matroid.
Yeah.
And take a set which is maximal, like that is a maximal set. Right. Maximal, you got the idea, right? Yeah, that it doesn't exist on the independent set which contains it. Yes.
Okay. Yeah. Thank you.
Yes. So proof is simple only, but let's go to Kruskal's algorithm. So Kruskal's algo. So we are given a graph, and there is a weight on edges. So what does so Kruskal's algorithm? Let's go for max spanning tree. So anybody have any idea? Like should I? Okay, I will tell the algorithm. It's very simple. Everybody knows it. So what we will do? we will take, like I will write in like a normal, we will take max weight age, then if we will check that, then we will take that max weight edge, then we will check if it forms a cycle. If it forms cycle, if yes, then edge is not in our tree. No, then we will have it in our tree. Like the way to write this algorithm is very like not that good, but you get the idea. And then we will repeat again. So eventually we are forming, this is greedy algorithm because we are taking maximum weight edge, and then we are checking it is formed cycle or not. So which Matroid structure does this Kruskal algorithm need or have, like the graph? The graphic Matroid, okay? So you might remember, like I defined about the graphic Matroid. So in Kruskal's algorithm, we need, suppose graph is connected, we need a tree. And if it is a disconnected graph, then we will need a forest. So the graphic Matroids, the elements, the independent set of Matroid are sub-trees of the graph, sub-forest of the graph. So the graph have Matroid structure, and there is greedy algorithm. The greedy algorithm will give optimal answer, like from this theorem, like simple proof. Like you can state that this theorem implies Kruskal's algorithm will give optimal answer. Do everybody agree? Ranit, any doubts?
Yeah, I'm trying to see.
Okay. Take a minute, then ask that. First, assume that this algorithm is true, then think for Kruskal's algorithm. So we have a Matroid structure on the graph.
Yeah. Okay. Works. Sorry.
And we are given a greedy algorithm. We have given the greedy algorithm, which is exactly like this. Because we are adding an edge, and we are seeing if it belongs to independent set. So in graphic Matroid, the elements of independence are acyclic graphs. So eventually we are checking if it contains cycle or not.
Yeah, true. Works.
Yes. So greedy algorithm will give optimal answer. So let's prove the algorithm. Like proof is also nice. So one way using induction, like we are given a Matroid and we want to prove that the Matroid will give optimal answer. So let's suppose we are at, let me define, Si is set S, this set S till we have seen first I elements. So this is some notation. So Si is the set. After looking at the first I element, whichever the elements we are considering in the max weight base. So our induction statement is for every I there exists Bi, the basis, such that Si is subset of Bi, and Bi minus Si is subset of I plus 1 to n. So what does this tell? That this is exactly the statement of the algorithm. So we are at ith step, and we have looked around I elements, and we might not consider all the elements for our max weight base, but we will consider some of them, and we are hoping that that should be max weight base. So we are saying that for every I there exists bi, a base set such that si is subset of b, and the remaining element in bi are from I plus 1 to n, which means that the previous element that we have looked till I cannot be in the set. So if we prove this, then Sn will be equal to Bn. If the induction statement is correct, then if we move forward, Sn will be equal to Bn, and then this proves the statement that we got a max weight, like Sn will be basis, and we are choosing such that, and here, sorry, I want forward to mention, this is max weight base. Yes. There exists bi such that as a subset of n, b is the max weight base. So if we prove this induction statement, then we are done. Okay. Should I prove this induction statement, or I can leave it?
Give a rough idea if you want.
Okay, rough, simple. Let's go for S0. S0 is 5. So there always exists a basis such that this all properties are satisfied. Take any base, max weight. We know that there exists a max weight base. That take it. It will satisfy it. Let's go to ith state, I minus state. So we have Si minus 1, subset of Bi minus 1, where our above induction statement is satisfied. Now suppose we are at ith element. There are two cases, that Si plus I belongs to I, or Si plus I. I is the element in the ground set. And it is not sorry, it should be belongs, sorry, my mistake, doesn't belongs to I. There are two simple cases, right, at the ith state. Suppose this belongs to here. Let's first look at this case, that Si minus 1 plus I doesn't belongs to I. That means Si will be Si minus 1, and by the subset, and we can take Bi minus 1 is equal to, Bi notation should be like, and yeah, so induction statement is satisfied here, because Bi minus Si, which is equal to Bi minus Si minus 1, and we know that and we need this to belong to this I plus 1 comma 2, let me zoom it, I plus 1 comma 2 n, and so in I minus 1 statement, we know that Bi minus 1 comma Si minus 1 is subset of I comma 1 to n. So by basis, by first property, which property? 1 second, let me remove something. So we know that this is true, but how we are discarding the element I? Why I is not in, so we have taken this statement, I was not in, was I in, how we can disregard that I was not in? Can anybody help?
I was not in what?
So here we know that this is true, and we have taken Si is equal to Si minus 1 because we are not considering it. And so if Si minus 1 is a subset of B, and Si plus I doesn't belong to I, then where it is?
I doesn't belong to Bi minus 1.
My pen stopped working suddenly. 1 second. So Bi minus 1 plus I it won't belongs to I because of the subset property. Got it? So we are done with this proof.
Sorry, can you go over that with before another
Okay.
time?
No problem. Yes, I can go again. So we know this, and our case is Si minus plus I doesn't belongs to I.
Yeah.
So our Si will be Si,
Yes.
Si minus 1.
Yeah.
And let's take, and another thing, will I belong to Bi minus 1? This is question mark. Suppose it does, that I belongs to Bi minus 1, but this will compete with our exchange statement. Suppose this belongs to this, and Si is subset of Bi minus 1.
Yeah.
So Si plus Si minus 1I, or we have taken same name, should belongs to I by subset property. But
Yeah.
we have seen that this is not true.
Okay. So I
So,
want Bi minus.
Yeah.
Okay.
So I won't belong to Bi minus 1, and Bi, and we will take Bi is equal to Bi minus 1, and Bi minus Si is equal to Bi minus 1 comma Si minus which is subset of I to N from this induction statement. But we know that I doesn't belongs to Bi, so we will remove I, and so this satisfies our induction statement.
Okay. Yes.
Now let's move forward to our next case. So in our next case, we are considering that as I minus 1 plus I belongs to is an independent set. So now there are two cases. I belongs to Bi minus 1. Then we are done. We will take Bi is equal to Bi minus 1, and Si will be Si will be subset of Bi, and all the properties will be satisfied. Another case, what we will do when it doesn't belong to Bi minus 1. Now we want a basis set, max weight basis set, such that Si, our new Si here will be this, that Si, and so Si we need B dash such that Si belongs to B dash, and it should be max weight also to prove our induction statement. So I will remove this part. This is not necessary, and we'll prove it here. Okay. So now we want to by extension, like we can extend this Si. We can we can extend this Si. Like how can I say extended? Let me phrase in good statement. So we have taken this Si, and we will add elements. We have remaining n minus I plus 1 element, and we will add elements such that this will be part of some B dash, like extension of basis, like similar to linear algebra, that we extend a basis by adding new vector, exchange property, that we know. In there we will call it exchange property. So we will add elements in Si such that it will form a basis B dash, and as we have added element in Si, it will be subset of it. Now we want to prove that this, or we can say there exists a basis such that SI is subset of B dash. And now we want to prove that B dash is max weight. If we prove this is max weight, then we are done. So Bi minus 1 comma B dash, as we know that both are bases, so they, one second, I'm forgetting a step. Sorry, I had to check. I will be subset of I. Am I right? I will belong to B dash because we want such a set, because SI in B dash, I will belong to B dash, and it is basis, and we have I minus 1 such that I doesn't belong to it. So Bi minus 1 comma B dash will be a set I. Am I right? No, it's another way around. B dash minus Bi minus 1 will equal to I, because we know basis, and we know that is this statement right? One second. Okay, this is true. And then if we check other way around, Bi minus B dash, so there will exist some element, because they are not same. It will contain some element J, which is in Bi minus 1 but is not in Ba. So there exists J belongs to I to N, such that J belongs to Bi minus 1, but what's called J doesn't belongs to B dash. Now let's check at the weight of B dash. Weight of B dash will be a weight of, I think I made a mistake, like this is not me. Let me check which mistake I did.
So here B dash is the Metroid element you want to get, right?
So I think let me start again from here. The statement that I said we are extending SI, that was wrong. So
you still can extend SI, right? I mean,
we can extend SI, but I would like to extend Bi minus 1. So like some remove some element from B. We will how do I say it? Like I'm not getting some words. Okay, so we know that SI doesn't belongs to this SI, so we want such that B dash. So we are so let's again go to back again go to statement that we are extending SI from like SI will contains element of Bi except I and remaining element. So we are extending SI such that it become a basis B dash, and we know that B dash Bi minus 1 is I, and B dash also is a base, and cardinality of Bi minus 1 B dash is equal to 1. That is very, and so let's call this element, sorry, again notation. Let's sorry for the mistake, like I am doing this for second time, so I'm not clear. So we are let's call that element J, and B dash will be of form because of the basis property. We are considering another set B dash such that SI will be in some basis. So we are taking that B dash, and we are considering B dash such that we are removing an element from bi minus 1 and adding I. So because bases should have same size, so this b dash will be another base. D dash will be another base. And we know that bi minus 1 si is subset of I plus 1 to n. So j must belongs to I plus 1 to n. And weight of b dash will be weight of bi minus 1 plus weight I minus weight j. But weight I is greater than weight j. So let's call greater than equal to. So this implies weight of b dash will be greater than equal to weight of bi minus 1. But at that time we have considered this is a max weight base. So we already know that weight of bi minus 1 is greater than equal to any base. So from these two inequality we get that the b dash that we have created is the max weight. So we proved the induction statement and this should follow. Is everybody okay?
I have a doubt. Maybe
okay.
this is trivial. Why should b dash minus bi minus 1 exactly be only one element? Why should b prime?
Okay. I am constructing it such a way, like I forgot to mention that how am I extending here? I'm constructing it such a way.
Oh, you're making sure that b prime is like just one element more.
Yes. I forgot to mention that I'm constructing it. As I was saying, I can extend SI.
Yeah.
As that. Okay.
Yeah. Thank you.
No problem. Yes, it was my mistake. Okay. So we are done with one side. Let's go to another side. Another side we will prove by contrapositive. That we will assume that I is not matroid, and greedy algorithm will we will create a weight function such that greedy algorithm won't give optimal answer. We will prove the contrapositive part for other side. So suppose that our set E comma I is not a matroid. So when structure is not matroid, either of those two properties are not satisfied. Suppose the subset property, the downward closeness is not satisfied. So S is subset of T, T is an independent set, but S is not an independent set. So I have created a weight function which won't give an optimal answer in greedy algorithm. So let's run the greedy algorithm here. What will greedy algorithm do? So it will select the elements with max weight. So here which elements are with max weight? S. Elements of R have max weight. Okay. Element of S have max weight, but the greedy algorithm cannot select S because S is not an independent set. Let's say greedy chose S2. S2 is some notation that I remember. Let's A, which is subset of which is subset of E, and we know that A is not equal to S. Okay, because S is not an independent set. So A will contain there's suppose subset S1 of S belongs to A. So some element of S can belong to A, but not whole. Let's say that we call that set S1, and let weight of A will be weight of S1 plus weight of A minus S1. So, and we know this this is 2 times mod S1. So what will be the max weight of A minus S1? So the remaining element, so after looking at the all element in S, because we are looking at downward decreasing order, so this will go to T minus S. It will take elements of T minus N. So my question is, how many elements of T minus S can it take? All of them? So this will be less than equal to 2 times mod S1 plus weight of, sorry, less than equal to mod T comma S. Am I right in here? Let me check. Got it? So I have taken by according to greedy algorithm, I might have taken some element of S, which I will call them S1, and then what are the remaining from where remaining element can be taken? They can be taken from T minus N, and maximum how many can be taken? T mod of T minus S, and we know that from this statement we know that less than S. So isn't it the exactly weight of T? Can you see? Do everybody agree? So we are running greedy algorithm, and we will obviously take max weight elements. So we will take some element from S, call them S1, and the remaining element we can take from T minus S because they have some weight 1. So at max we can take T minus S. So our total weight will be at max weight of T. And this should be, I think, this shouldn't be, this should be here, less than here, because weight of this. And also, it cannot take all the elements of T minus S. It cannot take all the element of T minus S. It can it? It won't take. It can take. It can take. No problem. No worry. So we.
So is T an independent set or T minus S is independent set? Like
T is an independent set. S is subset of T, and we
S
don't
is
know about.
S
We
is
don't know
not-
about T man.
Okay.
So we are considering that E is not Matroid. So we are violating the condition what? That there is a subset of T which is not an independent set, but T is.
Oh, okay.
And we are creating a weight function and applying greedy algorithm with respect to gate function. And this, so we came to know there exists a weight function which doesn't give optimal structure if the underlying structure is not Matroid.
Okay.
So this weight function,
Give an example of some S and T such that T is independent but S is not independent.
okay, let me check. Can we go here?
Not able to see.
No, in Matroid it won't satisfy. Like
yeah, in Matroid it won't in general some two sets.
Okay, I will include in this union. Let's take as T is an independent set, but the subset is not because we won't structure won't go to Matroid. How can I say?
I am not able to see such a thing because I feel like if T is independent, the whole subset every time will become independent. Can it be such a case?
Yes, good question. Let me think for a minute. If it is a Matroid, then it is.
Yes. If not a Matroid also, I am not able to construct. Like any set, if I'm saying it's independent, I'm imagining its subset also to be independent.
But then you are
So like,
assuming the Metroid is true. But if you take like a
Ah,
Metroid which is just a single element set, let's say
okay.
some uh, set I, and there is no phi, then it's not a Metroid, and the condition doesn't hold.
okay, so Padmapriya, as Praneeth said, let me remove this element from here.
Oh,
Which element? These elements.
okay.
Let me remove them. Now take this set. We got
Okay. Oh,
it
in
just.
the
Uh,
hmm.
it was just simple removing some element, as Praneeth said. So we are done. So this is some structure that we have given, and it doesn't satisfy the downward closeness property.
Yeah, yeah.
So this was our case 1. Similarly, for case 2, it doesn't satisfy the exchange property, that both elements are independent set. One of them have mod less than this, but for all I belong to T minus n, S plus I doesn't belong to I. Simple. So what will what will a greedy algorithm do? Here, greedy algorithm will take S whole, S itself, and this will be mod S. Greedy algorithm will choose the H set, but it won't choose any element from T. Why? Because any element from T minus S plus I doesn't belong to independent set, so it won't take any element from T minus S, and remaining element it can take if it form matroid, but it doesn't change the weight. So this will be equal to mod S plus half. But now uh, weight of T will be mod of T. Mod of T, okay, it should be mod of T. Mod of T, sorry, mod of T minus S, and this will be less than equal to. So it mod of T will be mod of T minus S plus mod of T intersection S. Agree? Mod of T intersection S. And let's verify this weight. How does it looks? So I have to simplify this in form. Okay, this will be mod of T minus T inter. This is some simple calculation. And we know that this so and weight of T is greater than mod T, which is greater than mod S plus 1. Can you see? So weight of T is greater than equal to mod of S plus 1T, because we consider that mod T is greater than mod S. So weight of T, by calculation we found out that it is greater than mod T, which is greater than equal to mod S plus 1. And we know that an greedy algorithm will always choose elements from S, and its weight is mod S plus 1. So again, we got greedy algorithm chose an set which is not optimal. So do people agree with this proof? Yes. That's all I had. Thank you. If any doubts are there, you can ask me.
Like, do you have any references for this? Like, to refer to?
Yes, I have many references for this. So like which type of like the part that I was said the things there are so many more things about Metroid. There is something called rank function of Metroid. The rank function of Metroid is some submodular function, and submodular function is some very important thing in like in it come in what's called that in machine learning also it is very important in very discrete structure combinatorial optimization algorithm it is very important. So Metroid so there are so many aspects of it like which you want to go like this whatever I told till today or anything else.
Okay, like this summer I'm learning like machine learning, like so anything useful to that? Like you're seeing something?
Yes, it will be useful. It won't be directly useful because there is a rank function. Let me define rank function of Metroid. Rank of Metroid. Rank function of Metroid. Okay, rank function. So let's take subset of E. Rank of A, the subset of ground set is max mod let's call S as subset of A and S belongs to I. So the rank function of for Metroid which will give a number associated to every subset of E. So how did we define? We look at all the independent set which are subset of A and we take the one with maximal cardinality. The maximal cardinality will be our rank of it. So this function is a submodular function and submodular is more general function. Submodular function let me give definition of submodular function. So submodular function satisfies a property that we have a set let's take a set A, a set B and A is subset of B and f of A plus I minus f of A so if we make a small if we make a change in A, f is a function submodular function. So submodular function are like that. If we make a change in small set, it will have bigger change compared to bigger set. You got my point, Dinesh?
Yeah, I got it. Yeah.
So this is the submodular function, and this function is somehow the maximization and minimization function is used in machine learning.
And but like I think this only works for discrete optimization, right? No.
No, you can have continuous optimization with this. Like you can extend this submodular function to a continuous space also.
Oh, okay.
So in the discrete optimization of this a maximization problem of submodular function is very tough, NP hard. So what people do, they extend it to a continuous space and then they use it. And I think that part is used in machine learning.
Okay.
And rank of a Matroid is such a submodular function. Yes. So I will give you a material like which will be proof for this algorithm. And the definition of Matroid, for definition of Matroid, you can directly do a wiki. No, I will share a presentation of it. So I will share the two documents. One will contain basic information about Matroid and second will contain the proof. Yeah, that's all. Anything else?
Where are you using all of these things in what you're doing for masters, and like where is it in very algorithmic way coming in, except for this greedy? Is it primarily for a greedy understanding, greedy algorithm understanding?
No, like the rank. So I was working with some modular functions. So in algorithm, the problem that I am solving, I have cost functions are my the cost functions are submodular function.
Okay.
And rank of a Matroid is one of the examples which are easy and which are easy to work with compared to general submodular function.
Hmm.
So I was using the rank of partition Matroid, rank of uniform. So I was giving a Matroid structure on my problem and taking its rank function, like rank function is the cost function, and try to optimize. Like I wanted to minimize the cost. So these were some examples that I used.
Yeah.
So
How is this method like better from like the conventional convex optimization type LP, linear programming, SDPs compared to
no, I am doing those things only. LP, SDP is convex programming, but in the cost function are the rank of Matroid. Like this is just the property of Matroid.
Okay, okay. Yeah.
So like while I was working with this, I was very surprised that for a greedy natural algorithm, we have some structure like if and only if condition. Like initially it
Yeah,
was
I
very
too was
vague.
surprised.
Yes. So that's why while I was studying for rank function of Matroid, I came across this. I was in general studying Matroid. Then I found this very interesting. That's all.
Oh, nice. So these kind of problems which have like underlying Matroid structure, are they like easier to solve with these LPs and all of these? Like, it's because it as a like, okay,
Because greedy algorithm works, that we proved. If it have
that's nice.
yes, it depends on the like what you are asking for from the Metroid.
Okay.
Like if you are asking like if you want to find max independent set,
Yeah.
then this algorithm will work. But you are asking some another question from Metroid, then it won't work. Like depend on the question. Here we found the max independent set, max weighted.
Yeah.
And this is useful in many things like Kruskal's algorithm. Like this is give characterization for Kruskal's algorithm.
Nice.
Yes.
Yeah. Nice.
So if somebody asks for Kruskal's algorithm, then you can give this proof like Matroid proof.
Yeah.
Yes. Yes. Anything else?
So these are like these work only to find out sets of small size or big size when they don't have many conditions on them, right? For example, if I say I have to pick a dominating set uh,
Mm.
where every neighborhood of each vertex in the graph has a unique neighborhood, uh, then can you think like how would you use it?
So first we will need a Matroid structure there. Do graphic Matroid work there?
Okay, okay. So
Uh,
like every method structure. Okay, 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 okay.
so if
Okay,
when you
yes.
are forming a Matroid structure, think about independence. Like as in linear algebra, think about independent. Like how can we form an independent set? So most natural thing that came to people's mind that was graphic Matroid that I have discussed. That in which we take acyclic graphs.
Hmm.
So take many acyclic graph, you can put together and you can form whole graph. That kind of basis kind of thing like linear addition of linear like addition. What's called that? Addition of vectors similar to that.
Okay.
So this property was satisfied by this was underlying structure for the Kruskal's algorithm. It worked,
Okay, okay.
and there are many more things in which like this will work.
Can you suggest a source where we can see about graph problems in Matroid structure, like procedures?
Okay, that currently I don't know. Like I just came across this one example, and like mostly the things that I'm working with, I'm not working with graphs. So currently I don't have idea, but I have a document. Let me see one second. Where it is? Is this it? Is this?
Like I found a PDF online by James Oxlade. I think like that is more graph theoretic approach.
So can you screen share now? Like Can you
Yeah,
share
I can
with
share
me?
it to Praneeth. Yeah.
Okay, okay, ठीक है, share it. Otherwise, I said you
can
can
also
share it
put
now.
yeah, link here, no, in Google
Hmm.
Meet chat.
I had a document from a convention, but I don't know where it is now. I got it. Okay. Metroid Basics by Saket Sorrow. This just gives Pushkal algorithm. Metroid Gray, examples of Metroid, graphic Metroid Y, transversal matrix. Yes, there is some. So I also got a document which also talks about some bipartite also. Bipartite graphs are used. Linear Metroid representing. No. This the 2-3 documents that I have, they go in more abstract way. Like they directly don't deal with graphs. Hmm. So like Dinesh have some document he can share. Yeah, that will be helpful.